Math 2312, section 1.6, absolute value equations and inequalities. Yet another example of an absolute value inequality. As I stated in the previous video, I summarized the technique that we used to solve an absolute value inequality, which actually will solve most inequalities. Change it to equal and solve, partition the number line, test each interval, keep the true intervals. It really doesn't matter how junky the problem is. So let's attack this one. I invite you to pause the video and see if you can solve it. I'll warn you, I set up a trap. All right, let's pull it off. And if you planned on solving it, pause it because I'm about to solve it. All right, first things first, pretend it says equals. Absolute value of x plus 3 followed by plus 7 all over 2 is less than or equal to, we're changing it to equals, is equal to 3. And let's solve this. I'd get rid of the fraction first. Anytime you're solving an equation with a fraction, you can, at whatever time you want, multiply to eliminate the denominators. In this case, multiplying both sides by 2 would cancel the denominator, leaving the numerator on the left, and multiplying by 2 on the right side would give us 3 times 2, which is 6. Okay? Oh, by the way, the reason I didn't set this equal to 3 and negative 3, and I mentioned this in class yesterday, when you're solving an absolute value inequality, absolute value equation, we have a strategy for solving something that looks like this. Absolute value on the inside equals a number. This equation is not yet of this form because it does not say absolute value on the left. It says absolute value plus something over something. So we don't split into 2 equations and lose the absolute value until we get the equation to this form. And we're almost there because after multiplying by 2, we can get to this form if we get rid of the 7 by subtracting it from both sides. I feel like I should go back up here and write times 2. We said it, we did it, we never wrote it, but if I'm going to write the minus 7 move, which is kind of obvious, I think I owe it to the problem to write the times 2 move, which is the slightly more complicated move. 7's cancel, leaving an absolute value of x plus 3 equals 6 minus 7 is negative 1. All right, our next move normally would be to set the inside equal to this number and its opposite. But you may recall that when I gave you the procedure for solving an equation like this, there was an asterisk on the word number. Do you remember what that asterisk said? That asterisk said, if this number is negative, this equation has no solution. Just like here. You cannot take the absolute value of anything and get a negative 1. So what does that mean in terms of our flow, in terms of our procedure? Well, actually, it doesn't change anything. We keep moving forward. The answer to part 1, solve this equation, is that there's no solution. But be careful. When I say no solution, I'm saying there's no solution to the equation, not to the inequality. We haven't solved the inequality yet because we haven't done the rest of these steps. Now you might be thinking, all right, in step 1 there were no solutions, so how can I do step 2, which says take the number line and partition it? Well, previously we cut the number line in 2 places because there were 2 solutions to the equation that we solved. How many solutions were there to this one? None. So guess how many times I'm going to cut the number line? None. We take that number line, think of it as a piece of string, and don't cut it at all. All right, so the partition move is fairly trivial. We're done. There's nothing to cut because there was no place to cut it. But that doesn't mean we don't stop. Now we go to step 3, which is test each interval. Well, if I didn't cut this number line, it's still one long piece of string. And what's the interval that represents this whole number line? Negative infinity to infinity. This can and does happen with inequalities using this approach, where you solve and get no solution. But what that means in the next 2 steps is you don't partition the number line because you have no place to cut it. So you keep it as one big interval, and then you move forward. Speaking of which, third step is to test each interval. Okay, we need to pick a number between negative infinity and infinity. We have a lot of choices. I would choose something simple, like x equals 0. All right, let's test x equals 0. I'm going to go ahead and write the inequality with the 0 substituted for the x, but let me tell you what's going to happen. Excuse me, this is a 3 over here. One of two things will happen. This will be true or this will be false. If it's true, that means that every number on the number line is a solution. So the solution would be all real numbers. If it's false, that means nothing on the number line will make it true. So the solution would be no real numbers. So at the end, it's either going to be all or none, depending upon whether this is true or false. Let's work it out. In the absolute value is an addition. 0 plus 3 is 3. Still inside an absolute value. Write down everything else. Absolute value of 3 is 3. The plus 7 and the divided by 2 haven't been done yet. Still comparing it to the number 3. At this point, you can probably fast forward. 3 plus 7 is 10. 10 divided by 2 is 5. 5 is less than or equal to 3. Wait, no it's not. This is false. That means the interval from which the test value came is not part of the solution. That was the only interval, which means that the solution to this problem, because our fourth step says to keep the true intervals and there are none, the only interval we had made it false, so there's no solution. Now be careful. I don't want you to falsely draw the conclusion that no solution to the equation implies no solution to the inequality. It did in this case. But what if, and it wasn't, what if in the original inequality it didn't say less than or equal to, but it said greater than or equal to? That wouldn't change what happened here. That wouldn't change what happened here. And it wouldn't change, well, we could use the same test value. The only thing that would have changed was the inequality all the way down the line. And had it said greater than or equal to, it would have been true. This would have been a check mark. And instead of the solution being no real numbers or no solution, the solution would be all real numbers. Or negative infinity, comma infinity. So don't incorrectly stop a problem here if the equation has no solution. Again, usually what that means is your final answer will either be no solution or all real numbers, depending upon how the test value plays out in the original inequality. Could we have spotted this sooner? Yes, had we used the alternate technique specific to this problem, which doesn't put the equal sign in, you just start attacking the problem as is. But like I said, I want to focus on a universal technique that always works. And I'm going to do one more example of how this technique is universal in the sense that it can be applied to other types of inequalities besides just absolute value.